Good afternoon, everyone. This is Mohan from Triple E Department, and today my topic is about leakage current detection in high voltage systems. Leakage current detection in high voltage systems, comprehensive overview and methodologies, definition and importance of that leakage current refers to the uninterrupted flow of electric charge through insulation or across surfaces in high voltage HV systems. Detecting it is crucial for ensuring safety, preventing insulation degradation, and maintaining system reliability. Sources of leakage current. Common causes include insulation, aging, moisture, increase, contamination, and partial discharges. These factors can increase dielectric losses and compromise equipment integrity. Scope of study. This presentation explores detection techniques, instruments, measurements, methodologies, and applications in power transmission, substance, and high voltage testing facilities. Industrial relevance. HV leakage detection systems are key in predictive maintenance strategies and condition based monitoring in modern smart grid architectures. Introduction under understanding leakage current in high voltage systems. Fundamentals and physical mechanisms. Basic concept, physical mechanism, impact on system reliability. Quantitative ranges. Why leakage current matters. Risks and consequences. Operational safety and economic implications. Safety hazards, equipment damage, system reliability and downtime, economic losses. There are four types of leakages currents in high voltage systems: resistive leakage current, capacitive leakage current, surface tracking leakage current, combined effect in HV systems. Here in the resistive leakage current, it is caused by imperfection of contamination in the insulation material resulting in a conductive path that allows DC like current flow. It increases with insulation, aging, and moisture presence. Capacitive leakage current. This occurs due to the dielectric nature of insulation materials. Alternating voltage includes displacement current proportional to frequency and capacitance even in perfect insulation. Surface leakage current flows along the surface of insulators when contamination, dust, humidity reduces surface resistivity, leading to partial discharges or flashovers. In practical high voltage equipment, total leakage current is a combination of resistive and capacitive components. Analyzing their phase and magnitude helps assess insulation health. Causes of leakage current in high voltage insulation systems. Material, environmental, and operational factors. Insulation, aging, thermal stress, electric stress, and long term voltage exposure degrade dielectric strength, creating micro cracks and conductive paths that increase leakage current. Moisture increase. Water absorption reduces surface and volume resistivity of insulation, particularly in outdoor and underground systems, leading to higher resistive leakages. Contamination and pollution. Deposits of dust, salt or industrial pollutants from semiconductors, films, on insulation surfaces, enhancing surface leakage and tracking phenomena, mechanical damage and surface defects, physical damage, improper handling or erosion by corona discharge, weaknesses, insulation integrity, and introduces leakage channels, operational overstress, overvoltages, partial discharges, and thermal cycling accelerate insulation breakdown, further contributing to leakage current development. Standards and acceptable limits of leakage current in high voltage equipment. International standards framework, acceptable leakage limits, safety and compliance implications, testing and verification protocols. Measurement fundamentals, key parameters and principles. Accurate evaluation of leakage current in high voltage systems. Basic measurement principle, key parameters, AC versus DC measurements, environmental control. Instruments and tools for detecting leakage current in high voltage systems. Measurement technologies and field equipment, digital leakage current meters, clamp type or inline digital meters detect microampere level leakage currents with high sensitivity and wide frequency response, often used in live HV environment. Insulation resistance testers apply high DC voltage up to 10 kV to measure insulation resistance and leakage current, indirectly identifying deteriorating dielectric conditions. Partial discharge detectors, advanced tools detect ultra low leakages, event and transit discharges, providing early warning of insulation faults before failure occurs. Data accuracy systems. Modern setups integrates leakage current sensors with IoT enabled data DAQs for continuous monitoring, remote diagnostics, and predictive analysis. Methods and techniques of leakage current detection: direct, indirect, and circuit configuration approaches. Direct measurement method, indirect measurement method, bridge and null methods, modern techniques. Design of leakage current measurement circuits. Reference architectures and industrial implementation. Basic circuit configuration, isolation and safety design, signal conditioning and filtering. Industrial example, power cable testing, data interpretation and leakage current analysis, diagnosing insulation health and trend evaluation, understanding leakage patterns. Leakage current trends reveal the health of insulation gradually increases, indicate aging, while sudden spikes suggest contamination or partial discharge events. Therefore, determination, phase and frequency analysis, trend monitoring, and data logging. Practical challenges in leakage current detection, field limitations and mitigation strategies, electromagnetic interface, temperature and humidity effects, contact and grounding issues, measurement range and resolutions, safety consideration and precautions in high voltage leakage current testing, ensuring operator protection and system integrity, personal protective equipment, system isolation and grounding, controlled access zones, emergency procedures and monitoring. The future of leakage current detection in HV systems towards smarter, safer, and more predictive power networks, holistic approach to monitoring, digital transformation, enhanced safety and reliability, future outlooks. Thank you.